Good afternoon, class. Can you hear me?
Can, sir.
Yes, sir.
Thank you. Good afternoon to all of you. So, today we are going to start chapter 5. Very short one. I think we will finish very early today because this is the last chapter. The chapter not available, maybe will be uploaded week 10 or 11. If you need the notes immediately, you got to write down or just take notes quickly because I will go very slowly, extremely slowly. So you can stop me at any time as you like. If you need more explanation, please stop me and you can ask me. So we will start recording. Regarding other matters, you can ask me later on. So we start recording, yeah? Surjit Singh. Are you there, Surjit Singh? Suniljit Singh. Are you there, Suniljit Singh?
Yes, sir. I'm here, sir.
Very good, very good, very good. All right. So we will discuss other matters later. We have plenty of time. Just finish this part first. Very brief introduction about chapter 5. So if you look at the title, numerical methods for partial differential equations. So today I just want to give you a kind of philosophical explanations because we are not going to study the method today. The next lecture will be basically on the method, and the method will involve very huge calculation. So you need a calculator to do the experimental numerical computations, basically iteration. So today lecture not on method, but about partial differential equations. Because this partial differential equation, I think because there are two things here. Partial differentiation, one thing. Partial derivatives, which you already studied engineering mathematics 1. That is partial derivatives. But we are not going to study again about partial derivatives. It is about partial differential equation, PDE. So what does that mean? Is solving partial differential equation. So you may ask, what is this? So just to give you the background, you already studied chapter 1, chapter 2, chapter 3, chapter 4. But chapter 4 is about numerical method. But chapter 4, numerical method for what? The answer is numerical method to solve ordinary differential equation. So our concentration was solving the first order, chapter 4, yeah, by using Euler method, Yoon's method, Runge-Kutta method. So all of you know very well about three very famous numerical method, Runge-Kutta, Yoon's, and Euler to solve ODE, ordinary differential equation. Basically, this Euler, or Euler, Yoon's, and Runge-Kutta is to solve very complicated differential equation. What is the meaning?
Sir, are you
yeah.
sharing any slideshow?
Yeah.
We can't
You
see
go.
it, sir.
No, you go ahead. You go to the Ulearn, click the link.
Oh, okay, sir.
You go to you learn. Yeah, I am sharing. You go to you learn. You click.
Okay, sir.
Go to you learn. You click. I think Chia already got it. Win. Yeah, I already shared. Already shared. So we are in Microsoft Teams. So a very huge studies about the differential equation, but we have 5 chapters. So chapter 1 is about the analytical method. Chapter 2 is solving the second order homogeneous, non-homogeneous, and chapter 3 Laplace, and chapter 4 is numerical method for ODE. So chapter 5 is totally different. Why it is different? Because this is partial differential equation. It's another subject by itself. So when they say PDE, maybe you never studied before. But the word partial derivative you already knew from engineering mathematics 1. But that is just the name only, partial derivatives. It's not very much connected to that. But just to let you know, the symbol is the same. We use the del symbol for the partial derivative. Other than that, Chia, you already saw the slide, right? Chia, can you share the slide? Chia, can you share the slide, Chia?
Sir, because I don't have the slide, the chapter 5 slide in the ULearn.
Yeah, it's not available. So that's why I'm using mine actually. This is the problem. So you can see, but others cannot see. How? How do you get it? Huh?
Not really sure, sir.
No. How you can see, right?
Cannot see on the
But
screen.
it seems
Nothing on the
stuck,
screen.
sir.
Huh?
I will say some of them, some of us they are having blackout while the others are almost same as me, which is like it is lagging, so I can't see any next slide, sir. Just stuck in the I'm stuck in the overview there, sir.
Overview.
Yeah. Stuck.
Yeah, I can move the slide. Slide 4. I can move 4, 5. I already shared already.
Yes, sir. Sir, you did. But sir, you did. But for mine, my slide is stuck at the overview there. While some of the other people having blackout.
Oh, this is due to what? Internet problem.
There's a possible, sir.
Because I can move the slide, but you cannot move the slide because you have problem? Your screen not moving. After overview, slide number 3, right?
Yeah, still 5.1 and 5.2, sir. I'm stuck.
Then no, that is slide number 3.
Slide number 3, okay.
Slide number 4 is 5.1 introduction, learning outcome.
Oh, I see.
No, in my slide, I already sharing. But if I click stop sharing, you cannot see. You see, I'm using Team Microsoft is sharing a window. So I don't know what happened to Purushottamana. I already shared. What you asking?
Oh, so like this.
Yeah, please.
Like unshare and then share again.
Oh, stop
Yeah.
sharing lah. Then share
And
again.
then you share it again. See whether
All
can.
right. Oh, yeah. Wait. Okay. So I stop already. Now I go. Okay. Wait. Okay. Share. All right. You just wait for a while. Should have 1.5, chapter 5.
For me, I can see already.
Oh,
Nice,
who is
sir,
that?
nice.
For me, I can see already.
Who is that?
Yes, sir, I can see
Already
already.
can see already. Wong Chanji can see
okay.
already.
Oh, I see something problem. Yeah, you told me a good idea. I stop sharing and then share again. Yeah. Yes, sir. Okay.
Yeah, Tan Lee Loon's idea.
Who is that?
Tan Lee Loon.
Tan Lee Loan. Okay. Well done. Thanks, Tan. Because this is not easy class. This his online teaching is very difficult for me. Yeah. Okay. So yeah, I hope things will get better. All right. So today let's take it easy. So today is nothing much. Just like a warm-up session. We do only the historical background studies about partial differential equation. So you see the title is numerical methods for partial differential equation. We are very sorry, this slide not available. So if you want, you just take note, take a piece of paper, just do scribble enough because this is not about method. And the slide maybe will be uploaded week 10 or week 11. Now we are in week 9. Maybe most possibly next week, week 10 or 11. So slide number 2, you see that the keyword is a partial differential equation. So we want to know what is this. That is the main agenda for today. So this chapter is very short, but the 5.2 is very long, about 55 slides, which will go for until next week. We plan to finish the syllabus by next week. So today, see the red color, 5.1. Introduction. 5.1 is the introductions. And 5.2, we don't do it today because this is involved method, finance different methods for solve the heat conduction equation, which is very important for the mechanical engineering. All right, so we move on to the learning outcome. So that is define or identify or recognize partial differential equation. Since it is new to you, the PDE, new means the partial differential equation, yeah? So this one is a very huge studies. Most of you, since all of you are in mechanical engineering, this one it will be very useful for your future studies, project, research, master's, PhD level. You can take up this topic and solve the engineering problems. It's a vast opportunity here to do a research project or finally a research, or you want to write journal publications, books. But this is the beginning. So we are not going to study in detail about PDE. And the PDE, partial differential equation, is not same as ODE, ordinary differential equation. Not same means they have their own model equations, which involve the partial derivatives symbol. But the difference between ODE, because ODE, they have very precise method, analytical method. But PDE also can be solved analytical method. But what you studied in chapter 1, 2, 3 is about analytical method to solve ordinary differential equation. And chapter 4, you use numerical method to solve ODE. So for ODE, you already knew both analytical method and numerical method. That is ODE. ODE, you know, like Laplace transform, yeah? This is analytical method. And then you solve Euler. So what is different between Laplace and Euler? Laplace method is analytical method. And Euler is numerical method, but solve same problem, ODE. So you already knew both. But for this PDE, you don't study analytical method. No, answer is no. This one you have to study maybe in numerical method or numeric analysis course. That is not what we are going to do here. Here only numerical method. So that is the difference. ODE, like you know, Bernoulli, Cauchy-Euler, constant coefficient, homogeneous, non-homogeneous, all solved by Laplace transform and Wronskian method. All that methods are called analytical method, precise. But Euler, you just focus on first order ODE, which we already solved by using separable, linear, and exact, non-exact Bernoulli. So what is the problem here? PDE, you don't study the analytical methods. So that is the thing. So we want to focus on numerical method only in this course, the 5.1. So the learning outcome is get to know what is PDE, partial differential equation. And then, as I said last time, identify format, method, and get the output, if more. So once you already define, the second thing is recognize. This recognize, we use the word identify in chapter 1, chapter 2, chapter 3, chapter 4. Identify. The recognize here is different. Recognize the difference between, we have 3 types of partial differential equation. One is called elliptic. You know the word ellipse. Ellipse, that is single dimension. Ellipsoid is ellipse is 2D. Sorry, ellipsoid is 3D. But here we call it elliptic. It's the name of the equation. This is the mathematics, elliptic. But what this elliptic equation, the PDE, the form elliptic represent in engineering, that is what you're going to see later. Because elliptic, what is that? What is the equation which is related to engineering? So this elliptic is scientific name. But the technical name, the engineering name for elliptic, we will show you later. So you must know the difference between elliptic, number 1, number 2, parabolic. They are not same. You know the shape ellipse, ellipsoid, the rugby ball, paraboloid, the cup. holding the water. And then hyperbolic. This hyperbolic, from the word hyperbola. So hyperbolic is different from parabolic. You know the geometry. You can see later on. You can check the geometry of that. But here we are not going to do the geometrical kind of thing. Just to let you know, you must remember this. What is elliptic, parabolic, hyperbolic in this topic, PDE, partial differential equations. So we have to recognize. So how to recognize? Now, what is PDE? An equation involving partial derivative on an unknown function of two or more independent variables. Unknown function, the word unknown function is called output. Output. Output is unknown. And the known function is called independent variable. Known, that is input. So we have two or more independent variable. Actually, independent variable is the input. The unknown function is the output, because you are searching for the output. Input is the independent variable called partial differential equation. So the partial differential equation created from the partial derivative of unknown function of two or more independent variables. So what is this, class? So these wordings sometimes doesn't give you a very clear picture. The clarification is very difficult if just you have the story of this. It is good to explain, but more importantly, we need the equation. So you see the example. Try to understand. We will show you the general form later. If you want to take the notes, you can copy. I can wait for you if you want to copy for the time being. Just scribble only, just scribble rough notes. So what is this example, class? This example is partial differential equation. You can compare this equation with the separable. You see, not easy. This is second order. First order also included. We will show you later. This is second order PDE. It's not easy to solve numerically as well as analytically. You cannot use the method that you studied chapter 1 up to chapter 4 to solve this. Euler method, Yoon's method, or Rangikuta method. Cannot. So you have to study new method, how to solve. I always use the word iteration in chapter 4. At that time, maybe you didn't pay attention because you don't care very much on the iteration, because you repeat the process. You do a few steps because they are talking about steps, and then you get the answer, whether Euler or Yoon's or Rangikuta. But in this topic, the word iteration is very, very important, very significant, because you have to do a lot of iterations. That is the difficult task, but by using calculator, you can able to do the iterations. So what is this PDE? So we read this equation like this: del squared u del x squared plus 2xy del squared u del y squared plus u equals to 1. So this equation, whether elliptic or parabolic or hyperbolic, we do not know now. You have to wait later. So we just focus on the three types only. We call it types: elliptic, parabolic, and hyperbolic. So what is del squared u del x squared? The u is called the unknown, the output. the X and Y are called inputs. So you may not be knowing the independent variable, dependent variable, that is in mathematics. So independent variable is the inputs. So here we got two independent variable. What are they? X and Y. So your U, the output U, depend on U, X and Y. That is the answer. It can be solved by analytically, which we are not going to do that in this subject. We can solve this by numerically. So the numerical method is the what we call the approach that we are going to adopt. Okay, example, the next one. Next one is the third order. Third order involve U output, X and Y are inputs. So del cube U, del X squared del Y, plus X del squared U del Y squared plus 8U equals to 5Y. So this is one form of partial differential equation. So you can see the two examples here. Just to for you to be familiarized. You must be very familiar with this because this one is totally different. You see in chapter 4, quite interesting, some of the problem first order, we solve it using the separable and compare the answer with the Euler, like that, or with the Yun's method, or with the Runge-Kutta. That is the advantage for the chapter 1 to 4. But in this chapter, it's very hard to do comparison because you have to study the analytical method. But that is not in the syllabus. So these two examples is the sample or example for PDE, short form. So whenever they say the acronym PDE, capital PDE, stand for partial differential equation. Now we move on to the type, which you saw in slide 4, elliptic, parabolic, and hyperbolic. So we go to slide number 6. So many things here, they cut short and they simplify. So we see the general form. So if you have any question, please let me know. Roger Wong is sharing. So for this chapter, again, we only handle linear and second order only. So what is linear? What is second order? So that is the question. So for this, you have to wait. We see the form or the type of PDE. For two independent variables, that is X and Y, such equation can be expressed in the following general form. From general form, you transform the particular form. The particular form is the elliptic, parabolic, and hyperbolic. So you cannot go into elliptic, parabolic, hyperbolic straight away because there may be got other forms also, but you just concentrate on 3 forms. But in reality, there are not only 3 forms, maybe more than that. So for these 2 independent variable, 1 dependent variable, that is U, function of xy, that is the output. But the form of PDE is like this. This is a shortcut formula. What do you mean by shortcut formula? A, capital A, del squared U del X squared plus B, del squared U del X del Y plus C, del squared u del y squared plus d equals 0, A, B, C are functions of x and y. Or we can call this A, B, C are constant, also possible. This is a general term, functions of x and y. A, B, C, capital A, capital B, capital C are the functions of x and y. And the D, you see, this is a short form. If you expand D, it will be a function of x, number one, y, u, del u, del x. This is first order, and del u, del y. So they shorten it all this. They cut short all this. They put it in D. Why? Because this is a simplified form, easy to see. So if you write all the terms, it will be very, very long. You can write if you want, but it is not necessary. So we need to know A, B, C, and D. So by calculating the value A, B, C, D, then we will know whether the PDE is elliptic, parabolic, and hyperbolic. After that only we move on to the method. So method is not our concern for today. So today basically is what is general form? But before that, our focus is linear second order. This is linear. A, B, C are constant, then second order. So all you see the derivative are power 2, del square. This is a mixed derivative, you call it. You studied in engineering mathematics 1, the partial derivatives. This is called mixed derivatives. But that is a very small thing. But what you're going to do here is a very hard one because we want to solve numerically. So this is not easy class. Okay, so today we just familiarize ourselves with the form. This is called general form. So you must know this general form. Include 1, 2, 3, 4 terms on the left hand side. Right hand side, 0. Anything on the right hand side, you have to put it back left hand side. Or sometimes they want to bring some terms, for example, del u, del x, del u, del y, from left to right. It is up to you. But when they write general form, this is the simplest way of writing. This very nice form. That's why we call it NICE. The right hand side is 0. But when you see the problem, it will not be in this form. But that doesn't mean that we cannot solve the problem. Just the format is different. You see, even you look at the books, reference books, this formula, they write in various forms. But that doesn't mean that all different will give you different output. No, all will give you same output when you solve that particular problem. Only the problem is the way they interpret it according to the author's liking. So some authors like this way, some authors like another way. But if you redo again and you compare, all will be the same. So now we move on to our topic, as we said, elliptic, parabolic, and hyperbolic. What is this class? So this is our concern, elliptic, parabolic, and hyperbolic. But this is a technical term. More precise term in real world application is, we have another name for that. Okay. So now you see the table. This is called table 1. Categories into which the linear second order partial differential equation in 2 variables can be classified as follows. So you see the first column, b squared minus 4ac. That b squared minus 4ac, we are referring to this a, b, c. We don't worry about d. This a, b, c only. So you know in algebra, when you solve ax squared plus bx plus c equals 0, the quadratic equation, the roots, the solution x can take three forms. One is complex root, the other one is equal real roots, the other one is two distinct real roots. So similarly here, the b square minus 4ac, if it's less than 0, then it becomes elliptic. That is the answer. So what is this elliptic? This is called the category of the equation. But what is that in real world engineering application? This is what we call Laplace equation. Not the Laplace that you studied in chapter 3. Yeah? That is a method discovered, invented by Laplace, the name of the person. But this equation also discovered by Laplace. But this is PDE, partial differential equation. Laplace equation, steady state with two spatial dimensions. That means the x and y. So how do you read this equation? Del squared t, capital T over del x squared plus del squared t over del y squared equals 0. The output is T, capital T, stand for temperature, function of xy. What is xy? Xy is the, for example, distance travel. So this is what we call steady state with two spatial dimensions. That means the xy are the dimensions, the space dimension. The output is temperature. So in this case class, if you want to calculate A, B, C, A is 1 and your B 0 and your C is 1. That is the answer. Del squared U over del squared, A del squared U over del x squared, B 0 plus C del squared U del y squared, C1, D 0 equals to 0. So your A and C is 1, your B is 0. You substitute. You compare this equation. You compare this equation with the general form. This is what we call particular equation. This is the engineering equation. But this one is the mathematics equation. This one is developed by the scientists. It's a general form. So your B is 0. So B squared minus 4AC, calculate. B 0 squared minus 4, A1, C1. So answer is minus 4. So minus 4 is less than 0. So it is called as elliptic. If this condition satisfied, then elliptic. You see, before this slide, you don't know how to classify. This is called classification. Category is called classification. So you don't know how the elliptic is defined. So the criteria for elliptic is B squared minus 4AC must be less than 0. Then it is called elliptic. So you go back to that equation. In this case, your U is temperature. That is a real world problem. The U is the temperature, capital T. So del squared T del x squared plus del squared T del y squared equals 0. This is called Laplace equation. Laplace equations. So how to solve Laplace equation? That is what we want to study in the next lecture. So this lecture, we want to introduce to you what does mean by PDE, partial differential equation. So the PDE is a general name. Now, very specific, very particular name, Laplace equation. So Laplace equation means it must take in this form. Now, B square minus 4AC equals to 0. Then it is parabolic equation. So B squared minus 4AC equals to 0. So in this case, it involves the first order derivative. B squared minus 4AC equals to 0. That means your B can be AC can be negative also. So B can be 0. B can be 0. A can be A, you can put any value, and then C, you can put any value. If equals to 0, then it is parabolic. You can test this, equals to 0. B, there is no B here because del T over del T. Temperature depend on time. Capital T is time, temperature. Write down, yeah. Capital T is temperature. Small t is time. X is the distance, space distance. So the capital T depend on time and distance, small t and x. So del T over del T, that is here. This one, del U, del X. It is in D class. So in this case, maybe your BC can be 0. So your A, maybe this is K dash, yeah, K dash. So we don't have the value here. So you have to put some value, K. Then this become heat conduction equation. That is the name. So it is very important for mechanical engineering student because this is heat conduction equation, very useful. This equation is time variable with one spatial dimension. So time variable is the small t. One spatial dimension is the x. So that is the input. Actually, we have two inputs, small t and x. Capital T is the temperature, the output. So in this case, the B square minus 4AC must be equals to 0. Equals to 0. If B is B square minus 4AC equals to 0. It can be any form class, B 2 squared 4 A1 C1, for example. But they have to rewrite in this form. That is the thing. So this is one example. But if it satisfies this equation, B square minus 4AC equals 0, any equation satisfy this equals 0 is parabolic. But here they are giving one example. This is not general. This is heat conduction equation. Del T over del T equals to K dash del square T del X square. One example. Okay, now B square minus 4AC greater than 0. Then this become hyperbolic. B square minus 4AC greater than 0. Let's say B is 3, is 9 minus A1 C1. So 9 minus 4 is 5, greater than 0, for example. Yeah. Then this equation is called wave equation. When it is hyperbolic, that is actually hyperbolic is the scientific name. So the real application, engineering application, we can use the word wave equation. This is time variable also with one spatial dimension. Time variable is t and the x is spatial, that is the space, that is distant. So how does the wave equation looks like? Wave equation is del squared y del x squared equals to 1 over c squared del squared y del t squared. So the c is the constant. That's why we do not know the value. But the c will be given. For example, c is 2. So if c is 2, you have 1 over 4. Then we can solve this equation numerically. Find the y. X and t are the inputs. So you will be given x and t, the starting point, and then you do the iteration until you satisfy some criteria to get the y. In this case, y depend on t and x. time and the space. Space here means the distance. So b squared minus 4ac less than 0 is elliptic. B squared minus 4ac equals to 0 is parabolic. B squared minus 4ac greater than 0 is hyperbolic. So our concern is we want to solve these equations, class. But not all, we will pick one of them. So we have a lot of limitation here. So we assume that if you can solve one of them is enough. The rest, you can do it in the future. So we will focus on one of these equation and try to develop the method. And the method is not easy because this is not ODE. It's not like linear equation or exact, non-exact or Bernoulli, where you have very nice steps method. So we can solve this numerically. Okay, so now we move on to the explanation on elliptic, parabolic, and hyperbolic. The next slide, yeah, slide number 8. So what is this elliptic equation for you, for engineers? So elliptic equations, the b square minus 4ac less than 0, are typically used to characterize steady state system. This is another application. Steady state system. Where do we apply? So these equations are employed to determine the steady state distribution of an unknown, the output, in two spatial dimensions. That is your x and y. So the u, in this case, capital T is the temperature output. This is unknown, depend on the inputs are x and y. So x and y are the two spatial dimensions, elliptic. Yeah. What about parabolic? Parabolic equations determine how an unknown varies in both space and time. Parabolic. Unknown, in this case, unknown is your capital T. And the known variable is time and distance, T and X. So that is the meaning, T and X. Parabolic equation determine how an unknown, that is temperature, capital T, varies in both space and time. So space is X variable, small t is the time variable. This is manifested by the presence of both spatial and temporal derivatives. Temporal derivatives. So the time and the space. So you have the output, capital T, temperature. So hyperbolic, that is your y is the output and x and t are inputs, the c is the constant. So your y depend on x and t. Now hyperbolic category deals with propagation problems. This is a propagation problem is very useful in engineering. So an important distinction manifested by the wave equation table 1 is that the unknown is characterized by second derivative with respect to time. The unknown is y characterized by second derivative. So del squared y del x squared equals to 1 over c squared del squared y del t squared. So unknown is characterized by second derivative with respect to time. So this is characterized by this time. So the y depend on x as well as y depend on time. That is the meaningless. Okay, with respect to time. Okay, now we move on to the heat conduction equation. So heat conduction equation, if you look at here, is parabolic. So our focus is about parabolic equations. Del T over del T equals to K dash del square T del X square. So the B square minus 4AC equals 0. This is already shown. And then it is a parabolic equation. So we want to study or concentrate on heat conduction equation. So for this, you are shown an example, a thin rod insulated at all points in between, yeah, except at its ends. So one hand, left hand side is hot and the right hand side is cool. So there are two types of heat conduction equation. In the previous slide, they put K dash, but you can put K, it doesn't matter. I think there is maybe typo error here. Del T over del T. Capital T is the temperature, depend on time, left hand side, equals to K is a constant, right hand side del square T del X square. So this is one spatial dimension. That means depend on X only, the second derivative. X is the input, the single dimension, X only. So the distance is X. But we have a two spatial dimension. That means X and Y, this one. Del square T del X square plus del square T del Y square. Both are heat equation, but our focus is on this only. We just focus on one spatial dimension. In the future, you can expand this to two spatial dimensions. So we want to solve heat conduction equation using numerical method. The method we are not going to do today. So we reserve this for the next lecture, how to solve the heat conduction equation, because it's very lengthy, about 54 slides. So it may go up to next week. The method. So today you familiarize with the form, identify, and then the model, method and output, we do it in the next lecture. So the heat conduction equation, you have the explanation. This is a physical explanation, hot and cool. And what is this? So we are given the values now. You see in this introduction, example, yeah, same problem. Heat conduction equation, at left hand side hot, right hand side is cool. So the heat conduction equations require initial condition, number one. At the initial start time, we call it start time, usually T0. This one, this is called initial condition. The capital T is the temperature. You want to find that. The start time T0, the X is a distance, equals to 0. So the temperature is 0 at time 0. And the boundary condition, this is different. So you have an initial condition as well as boundary condition at each end point of the spatial domain. Spatial means the X value are given. This one, temperature at time T at 0 distance. This is 100 degrees here. This one, hot. And then after 10 distance, 10 meter or centimeter or whatever it is, the temperature is 50 degrees Celsius. So here we show this diagram. So after 10 meter, the temperature is 50 degrees Celsius at any time t. So this is the values will be given to start off your solution procedure. So where to start? So in order to start, you must be given initial start time, and then the initial boundary condition, I, B, C, initial boundary condition, and initial condition, IC, initial condition. We call it IVP, initial value problem, IVB, initial value boundary problem. So that's why we have both, because this is PDE. So PDE, you have more the initial condition and the boundary conditions. So that's all for today class. Or you have any questions, you can ask, and other questions as well. First, any question on this with any slide, and then we move on to other questions. Yeah, Farah Diba just joined the meeting. Yeah. Okay, any question, class? So far. Yes, Natasha, thank you. So what about Sunil Jit Singh, any questions?
No, sir. All good, sir.
Okay, Natasha, no question. Wong Chen, Hui. If you have any question on test 1 and quiz, not quiz 3, quiz 2. Quiz 2 only. Roger is asking, quiz 3 cover which chapter? Quiz 3 is this week, right? 11th. 11th November, Wednesday. So quiz 2, yeah. Chapter 3 and 4, sir. Yeah, Roger is there. 4. 3 questions. MCQ. 2 from Laplace. From Laplace. You check 40 minutes. 40 minutes, Sunil did. Plus 1 from Euler. So how many of you submitted test 1 via email? 9 p.m. Check Yulen. Okay, 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 yeah, okay, okay. No problem. Okay, okay. Basically, all. What happened? Surya Ganesan has left the meeting. Okay, okay, no problem. Muhammad Nur Hadi. Okay. Can you make the duration to answer a bit longer? Yeah. Yeah, Christian, email. Christian, you should email him. I'm not sure. Yeah, I'm not sure at the moment. Yeah. You email him. Email to Dr. Mohana. Yeah, Sunil Ji. Yeah, you are welcome. Okay, class. So that's all today. Shall we stop here? Okay, Suniljit, I wish you all the best.
you